going to add in a couple to refresh where we left off. The limit as x approaches 4 of 7. What would that be equal to? One of them. So my function is y equals 7. That's a horizontal line at 7. When my x is going to 4, what's my y value? 7, because it's 7 everywhere on that line. So the limit of a constant was the constant. If I said the limit as x approaches 4 of x squared minus 2x, what would I do? Maybe look back at, this was our last slide. X squared minus 4x is a polynomial, right? And this tells us if it's polynomial, you can just plug in your x. So I can just plug in my 4 to my function. So we get 16 minus 8, which is 8. Much faster than making 2 tables. The same is true if it's a rational function. Okay, if I plug it in here, I get 4 plus 1 over 4 minus 3. So 5 over 1 is 5. As long as the denominator isn't 0. Okay, so if I get a domain error, I can't just plug in. So that's what we learned Friday, and that's kind of where we left off. So we're going to practice using that today. Let's look at the next example. So take a look at it on your own first and decide, can I just use my direct substitution property? It's a rational function. So does that mean I can just plug in my 1? No. Why? Bottom is equal to 0. So direct substitution says you can plug it in as long as it's not a domain issue. Okay, so let's use algebra. Is there anything I could do to this expression that might help me? X squared minus 1, if we factor that, it factors into x minus 1, x plus 1. All right, now one thing I am going to really be a stickler about. Have we calculated this limit yet? No, so you have to write it on every step. Okay, it doesn't go away until we actually figure out what the limit is equal to. So it's annoying, I know, you want to go fast, you don't want to write it down, but you have to. Especially as we go on, there's a big difference between a problem with a limit and without. Okay, so you need to write that limit. How does this help? So now we have the limit as x approaches 1 of x plus 1. Now that's just a polynomial, so now I can plug it in. When you plug in the 1, that's when the limit goes away. So the moment when I plug in, I drop that limit symbol. And I found out that this limit was equal to 2. No way I could have gotten that from the original. It just gave me 0 over 0, so we had to use algebra first, simplify it to get to that point. The reason that's legal is that the original function is actually a line with an open circle at 1. And so remember, a limit doesn't care what happens at the point, it's just as you're approaching it. So as I'm approaching it, my y is getting closer to 2 because the limit doesn't care that the point itself doesn't exist. And so that's what the next property tells us. If 2 functions are equal except for at that one point, their limits are the same. All right, let's take a look at this one. I want to find the limit as g approaches 1, where g of x is this piecewise function. Take a second and look at it before I discuss. See if you can figure out what you think the answer is. So what Toby is saying, if we think about this graph, it's equal to x plus 1 as long as x isn't 1. Right, so if you put in a 1, 2, that would be an open circle, but you're on this piece otherwise. So if you put in 0, you get out 1. If you put in a 1, you get 0. If you put in 2, you get 3. And at the point when x is 1, what are you getting out? Pi. Okay, does the limit care what happens at 1? No. If I am approaching 1 on this function, then I have to be on this first piece because it's everywhere except 1. So you're on the line x plus 1 as you are coming in towards 1, because the limit doesn't care what happens at the point, and that's just polynomial. So you can, plug in your 1, and 1 plus 1 is 2. So we can use the graph to support it, but if you caught that, the only time you get this pi is if you're equal to 1. Limit doesn't care what happens at the point, just as we approach it. Let's try this one. Can I just plug in? No, because I'm getting 0 on the bottom. So what do you think we should do? FOIL. Okay, 3 plus h squared means you write it twice. You get 9 plus 6h plus h squared minus 9 divided by h. So my positive and negative 9 cancel. How does that help me? Take an h out of it, and just left with 6 plus h. So now we can plug in 0. Once you plug in 0, your limit goes away. And we get 6. Question 6. So look at this one. Can I just plug in? No. Any ideas what I could do? So far we've done like factoring and reducing, but can I factor this? No. We did one where we multiplied it out, but I can't simplify the square root of t squared plus 9. Any other ideas? So you're heading the right direction, but maybe not quite right. What if this was flipped and the square root was on the bottom? How would you get it off the bottom? You can just square if there's not an equal to, though, where we multiply each side of the equation.
Take it. I don't know the actual.
Don't know the word.
The square root of t squared plus 9 plus 3.
Yes, the conjugate. So we need to get rid of that square root. But it has to be algebraically legal, so we multiply by the conjugate. The reason this is legal is if I do it on both the top and the bottom of my fraction, I'm really just multiplying by 1. All right, for a moment, it's going to look like we've made our problem harder, but I don't think we have. So if I'm foiling on the top, the square root of t squared plus 9 times the square root of t squared plus 9, drop the square root, and just give t squared plus 9. Plus 3 radical t squared plus 9 minus 3 radical t squared plus 9. What happens with those? They cancel. Negative 3 times 3 is negative 9. On the bottom, I am actually not going to distribute this, because ultimately it's that t squared that's preventing me from just plugging in the 0. So I'm hoping it'll cancel out. And if I want to cancel it out, I need it in factored form. So I multiplied out the top. I'm not multiplying out the bottom. What happens now? So then what happens with my t squares? So the limit is 2 equal to 0 of 1 over the square root of t squared plus 9. Okay. This is all right. Our limit laws tell us we can do the top and the bottom. It tells us we can bring our limit under the square root. And since it's just polynomial, you can plug in your 0. So we get 1 over the square root of 9, so 3 plus 3. And that turns into 1/6. So we have to do algebra to get to an expression where we are able to just plug in the x value, or the number we're approaching. It cannot give you a 0 on the denominator. Other situations we couldn't have would be like a negative under a radical, anything that violates a domain rule. So then once I got to that point, we were able to use our limit laws, which tell us it is legal to plug in. Any questions there? All right. We've talked about left and right hand limits. And remember, the overall limit only exists if the left and right hand go to the same number. So that's still true here. We might have to use that process if we are applying limit laws. So let's take a look at this one. Do I have a limit law that tells me it is legal to plug something into an absolute value? We have limit laws about radicals, about exponents, rational functions, polynomials. Nothing about absolute values. So I cannot just assume that it works. So I have to rewrite this. The absolute value of x. If you put in a positive number, what does absolute value do? Stays the same. So it's just going to give you x if x is greater than or equal to 0. You get the same thing you put in. If you put in a negative number, so if x is less than 0, what will it give me out? The positive. So it does the opposite of x if x is less than 0. Anytime I'm dealing with absolute values throughout the year, we are going to have to be able to rewrite it as a piecewise function, because we aren't going to have any calculus rules that apply specifically to absolute values. However, we can deal with the piecewise function. Notice it's not like the last one that we did where it was just equal to and not equal to. All right, if you think about this, we know it looks like this. Okay, you have two separate sections of your graph, so we are going to do the limits separately. I'm going to do the limit as I approach 0 from the left, and then I'm going to do the limit as I approach 0 from the right. If I'm approaching 0 from the left, that means I'm plugging in things smaller than 0. So I'm on the less than 0 piece, so that is the opposite of x. Okay, if I'm plugging in things negatives, the absolute value is doing the opposite. It's making them positive. Right, can you plug a 0 into that? It doesn't matter that we're approaching from the left. When you go to plug it in, you're just putting in this number. So it's just the opposite of 0, which is 0. Right. If I'm approaching from the right, that means my numbers are positive, so the absolute value isn't changing them. So again, I can just put in 0. Since those are the same, that means the limit as we approach 0 of the absolute value of x is in fact 0. Now, did I need all that work? Probably not. Could you guys have looked at that at the graph I drew and told me that limit was equal to 0? Yes. But when we have more complicated expressions dealing with absolute value, this is how we're going to approach them. Break it into the piecewise functions, do your left and right hand limits, and see if they match up. Questions there? Let's look at this. All right, I'm already telling you this one doesn't exist, but I want you to justify why. So let's start by looking at this expression. My board just froze. That's fine. If I have the absolute value of x over x, it's maybe a long day for me, guys. That's fun. Well, let's take a second, rewrite this without an absolute value while I restart my program. So, if you put in a positive number, the absolute value of x is just going to equal x, and x divided by x would be 1. If x is less than 0, the absolute value of x would be the opposite of x. Then when you divide by x, what do you get? Negative 1. Okay, if you're not sure, test out a number. If I put in 5, 5 divided by 5 is 1. If I put in negative 5, you would get 5 divided by negative 5, which is negative 1. How come I didn't put an equal to on either of those?
Because
Denominator can't be 0. So this function itself doesn't exist at 0. Does that impact my limit? No, limit doesn't care what happens at the point, just as we approach the point. So, if I am approaching 0 from the left, I am plugging in numbers smaller than 0. So that's the less than 0, and I'm getting out negative 1. What's the limit as x approaches 0 of negative 1? As we approach 0 from the right. positive numbers. So I'm getting out 1. So the limit as x approaches 0 of 1 is 1. So the overall limit since the left and right hand limits are different. Limit as we approach 0, the s value of x over s does not exist. If you think about it from a graphing standpoint, you put in 0, or numbers bigger than 0, you're getting 1, smaller than 0, you're getting negative 1. The left and right don't match up. So the overall limit doesn't exist. Questions on that one? I want to try 1, maybe 2 more examples. We'll see how long this one takes, and then I'll stop for today. How would we decide if this limit exists?
Left and the left, left
I have
and
to
the
do the left and the right. I want you guys to try that. So start your limit from the left and your limit from the right. You have to decide which piece you would be on for each. Which piece are you using? Because it's less than 4. So that's polynomial, you can plug in. Doesn't matter that you're approaching from the left, you just put in the 4. So 8 minus 8 is 0. As you're approaching from the right, that means your numbers are bigger than 4. So you're on the greater than 4 piece. Square root of x minus 4. Again, we can bring it under our radical, and then it's just polynomial over there, so you can plug in. Square root of 0 is 0. So, does our limit exist? Yes. The overall limit as we approach 4 of that function is 0. Right. I'm going to stop here. Tomorrow we will finish up this section. Today I have a handout for you. I would like this one done tomorrow. So your directions say you can use limit laws, table of values, but I would assume at this point you are probably preferring limit laws, a little more efficient than that table of values.
Yep.